name is Zoe Turner, and this is my Lab 3 for the black hole. So why do we do this lab? Well, we do this to calculate the net force of the components from observing the motion of a star orbiting a black hole to determine the mass of the black hole. And here I decided to add my results. So for FNet, I got 7.4 10 to the 40 newtons, FNet parallel, which is 2.7 10 to the 40 newtons, and FNet perpendicular, which is 6.8 10 to the 40 newtons. So some things to be reminded of when doing this lab is that we need to do Newton's second law. But since we don't know what FNet is, we split FNet into FNet parallel plus FNet perpendicular. And we multiply delta t into that and derive everything. So we could get dp dt, which is delta, which is p hat times derivative of f parallel plus f perpendicular, derivative of f perpendicular times derivative of p hat over delta t. And to know where it is speeding up and slowing down, that's why we use dp dt parallel to find that. And for direction, to know where it changes, that's we use derivative of perpendicular. And you can see my small model on the side on where FNet is pointing down and where FNet times delta t is also pointing down in the same direction. You can also see where the derivative of dp dt, perpendicular, and parallel. So here is a small video of my lab to show the model. And as you see when I run this program, you can see how as it gets close to the black hole, the forces are really pulling the planet into the black hole. And we're done. So in my data, I decided to calculate velocity using a list that holds all of the x and y components of velocity. And as you can see in the code, I did the x velocity at some type of index, so we start at 0, equals delta x over delta t. Also, in this part of section of my code, I did something very more similar to find the initial and final velocities. Finally, to compute the initial and final momentum vectors, we do the mass of the star times initial velocity. And in the final momentum, we do the star's mass also times final velocity. And now we'll go more into how we figured out the mass of the black hole. Well, we can find that by using FNet equals g constant times the mass of the star times mass of the black hole over absolute value of position squared. If we rewrite this, we have mass of the black hole equals FNet times absolute value of position squared over g plus mass of the star. And we can change out FNet with the FNet perpendicular plus parallel components that we have. And as you can see at the bottom, my black hole's final mass was 1.108910 to the 46 kilograms, which is very heavy. So for the first question, why is the net force and its parallel and perpendicular components different from the rate of change of momentum? Well, we can find momentum, and we had to find momentum to figure out what FNet was. So that's why it's different from the rate of change, because we didn't really know, we couldn't calculate the net force at that time, but we could calculate the change of momentum at the time. So instead of waiting to make a quick look at the black hole, we want to enter it. So what initial velocity would I need? Well, because of my mass, I had to enter to enter some type of orbital, I had to do 3.24 10 to the 6 meters per second was my velocity. If I saw that if I went slightly above 3.3 or below 3.2, that I was either that I completely missed the black hole or I got sucked into it. So that's how I was able to find my final velocity. Thank you for watching my video. Tune in next week.